Thanks everyone for sticking around to the end of the day. Excited to get to talk a little bit about technical work, but I was asked to talk a little bit about myself too. So we'll start with that and how I got into the position I'm in now, doing machine learning for inertial confinement fusion research. So my first exposure here to the lab was pretty standard. It was through a summer internship. Through the high energy density physics summer program. Prior to that, I've been a student at Texas A&M. I did a bachelor's degree in physics, nuclear engineering, master's in nuclear engineering before coming here as an intern. Internship was pretty cool. I worked with Luke Peterson sitting there. Made it a pretty fun experience. I decided to come back through the Livermore Graduate Scholars Program and actually completed my PhD with Luke as one of my primary advisors. Graduated in 2019 and transitioned to staff as a design physicist shortly thereafter. So since joining the lab as staff, I've worked on a ton of different things. A lot of them were just listed. A lot of it's machine learning themed, a little bit of traditional design work, designing experiments for the National Mission Facility, but a lot of people associate me with my work in machine learning and the development of a neural network algorithm called GEN that's been used pretty broadly the last few years. Outside of work, a lot of people associate me with horses. Maybe you've seen that horse before on Newsline. Every time someone asks for a photo of me, I send them one of me and my horse. So I'm trying to get him all over the internal websites. So maybe you recognize him more than you do me. But with that typical bio, it looks like I've had like a very linear career progression. I studied physics, studied engineering, went to grad school, got a job. In reality, it was a lot more nonlinear than that. I didn't think this is where I was going to end up. So I actually started studying at Texas A&M in the nuclear engineering department for financial reasons. I liked horses my whole life, and I knew how expensive they were because I'd owned horses through high school. So I wanted a stable job so I could afford to keep a horse. So that's what motivated me going to college, honestly. But once I started, I found out I actually really liked physics. So after my first semester at A&M, I decided to double degree because I liked physics more than I liked sleeping, apparently. It was exhausting, but would totally do it all over again, given the chance. I learned a lot. I did get into research as an undergraduate, which I'm glad that I did that. I did all kinds of weird things. I did some theory work in quantum optics and studying electrical discharges. I did some engineering work, working in a lab that built superconducting magnets for particle accelerators. And then I did some experimental physics, a lot of optics, spectroscopy, laser work. I actually applied to graduate schools 100% convinced I was going to do biomedical optics. So that's the only thing I was looking at for grad schools. I ended up going to Rice University to study applied physics. I still liked physics, but it turned out I didn't really like the hands-on lab work that I was doing. So I just was not super happy in that situation, not happy aligning lasers every day. And I ended up calling a professor back at Texas A&M in the nuclear engineering department who did computational work. I thought maybe I'd be happier with that type of research. So I went back to A&M, did my master's in kind of traditional radiation transport simulation modeling. I still wasn't super happy with what I was studying and decided I would apply to very top level MBA programs. And again, kind of going back to my reasons for starting school to begin with, financial, maybe if I could go to Stanford and get an MBA, I would, just go ride horses after my day job. But while I was waiting to hear back from those schools, I took a summer internship here at the lab, and that kind of changed everything. I kind of fell in love with physics and science and research, and decided that that's what I wanted to do. So it was a really nonlinear process in which I changed my mind again and again and again. And I won't lie, changing your mind that many times is pretty scary. Deciding to transfer from one graduate school to another was kind of scary. But I'm super glad that I did it. I'm really, like, if I did anything, I made any really good decisions for myself, it was to not settle for being like not super excited about my work. Because it's so much, careers are really long, and it's so much easier to go to work every day knowing that I actually enjoy what I'm doing, I enjoy who I'm working with. So that was my career trajectory to how I ended up where I am now. I didn't put anything in these slides calling attention to the fact that I'm a woman in this position, but I am. And if you looked at my colleagues that I work with every day, you notice I'm one of just a few, which is unfortunate and still comes with its own challenges. So the advice I think you've heard a lot of times already today is that good mentors are everything, especially if you're navigating situations that are challenging for one reason or another. I've really relied on people that have been around longer than I have to help me make decisions and navigate challenging situations. And I still, use mentors to get where I want to be in my career in the future. So find that mentor for you, someone who you can trust and talk to and bounce ideas off of and discuss challenges with, and be that mentor for someone else, because those person-to-person interactions is really what make your job fulfilling and worthwhile on the days when the science is just hard and frustrating and the code won't work correctly. The people are what keep me going. So it's a little bit about myself. Now I want to talk about the thing that I like talking about the most, which is actually machine learning and fusion research. It's probably the reason you're all sticking around to the end of the day. So in the next half of the talk or so, I'll talk about the inertial confinement fusion experiment that happened in December that you might have heard about on the news, and how we in the ICF program used machine learning methods to actually predict the outcome of that experiment before it happened. So if you didn't hear about it in the news, it was everywhere. You can Google, find a series of news headlines about this big thing called ignition that happened back in December over at the National Mission Facility. So this was a really big result, decades in the making. Hopefully in the next few slides, you'll get a brief overview of why it was such an exciting result. But most of the world is excited about it because fusion energy, if you could harness it for power production, could be game-changing for humanity, right? It's a very efficient energy source. There's a fun statistic here, is that 1 kilometer cubed of ocean water contains enough fuel that would produce the energy equivalent of the entire world's oil reserves. You could harness it. So it's a really powerful energy source if we can figure out how to make it routinely for power production. So that's why the broader world is really excited about it. Here at the lab, we're interested in energy applications, of course, but also basic sciences. We can learn a lot about materials at really extreme conditions. So extreme, you only find them at the center of stars by doing these experiments. So this is going to be a whirlwind overview of what is fusion and how do we model it and everything, but happy to answer questions after the fact and point you to resources to learn more. But very briefly, the experiments we do at the National Mission Facility are trying to achieve fusion ignition through a technique called indirect-drive, ICF. So in indirect-drive, we have this, use my cursor, we have this, oh, you can't see it on that screen. Okay. We have a gold cylinder called a horum. It's about the size of a pencil eraser, a little bit bigger. And that gold cylinder, we're going to turn into an X-ray oven. We'll heat it up with the 192 laser beams that make up the National Mission Facility by pointing the laser beams in to the horum through the top and bottom laser entrance holes. Lasers will turn on, they'll heat up the walls, they'll radiate X-rays, and those X-rays are what we're going to use to implode our capsule or compress it to extremely high temperatures, densities, and pressures. So inside this gold cylinder is our capsule. That's what contains our deuterium and tritium fuel. There's a cross section of it shown here in the middle of the slide. It has an outer layer called an ablator. Lately, we've been making those out of diamond. The inner layer is a layer of DT ice. That's deuterium and tritium fuel. That's what we're going to be fusing. And then there's DT vapor in the center of the capsule. So during an ICF experiment, our goal is to compress this capsule as much as we possibly can to get it to really high densities, really high pressures, to create conditions similar to what you'd find at the center of a star. So the deuterium and tritium begin to fuse. When that happens, they produce a neutron, an alpha particle, and a lot of energy. So very basic stages of the implosion are: one, you start heating up that capsule with your X-ray bath that you created with your forum. As you heat it up, the outer layer of the capsule, called the ablator, begins to ablate. It starts flowing off. As it does that, it creates equal and opposite force that compresses the inner surface of the shell radially inward. So you're compressing this spherical capsule, ideally in a spherical fashion, to really, really small volumes. At some point, you'll reach a minimum volume. You'll have squished this as much as you possibly can. If you set things up right, your deuterium and tritium will begin to fuse. You'll start producing a lot of fusion energy through these reactions. At some point, as you're producing heat through these fusion reactions, your fuel will start to expand and the whole thing will kind of disassemble and your burn will stop. The goal of all of this work is to create more energy through those fusion reactions than we're putting into the system with our laser drive. So these experiments are carried out at the National Mission Facility. It's a building not too far from where we're sitting here in person. It's a huge facility. If you get the opportunity to tour it, I totally recommend it. It's an extremely impressive feat of engineering. Several football fields in size. Where all of the interesting stuff happens, in my opinion, is inside this target chamber. It's about 10 meters in diameter, so it's still pretty large. But the targets themselves that we're actually imploding are super tiny. They're just a couple of millimeters in diameter, and they sit in this little gold can. So next we'll do a very brief timeline of some of the big advancements we've made in fusion research at the National Mission Facility over the last decade and a half or so of experiments. So early on when the facility first started doing these DT experiments, we were using primarily plastic ablators. We learned a lot about hydrodynamic instabilities. With these experiments, learned how to tailor our pulse shapes in order to mitigate these instabilities, and went from producing, very, very low yields in 2012 up to about 20 kilojoules in yield. So the y-axis here is the neutron yield as a function of experiment ordered by the year they were executed on the x-axis. So after we learned a lot about implosions with our plastic capsules, we decided to go to a slightly more efficient ablator, and we started using diamond ablators. That improved things quite a bit after a couple of years. By 2018, 2019, we had doubled the yields we were producing. We learned a lot about symmetry control and how to implode these capsules as symmetrically as we possibly can to be very efficient in our use of our laser energy. The progress started to really accelerate just a couple of years ago. With our better ability to control our implosion symmetry, we were able to increase the size of our capsule relative to our home, which makes the whole thing a little more efficient. And we were able to achieve the state called burning plasma for the first time ever in 2020, 2021. And this is kind of like the pre-ignition phase. Like you're starting to create conditions where you're really producing quite a bit of fusion energy, but you just need a little bit more of a boost to start igniting. So we got that little bit more of a boost in late 2021 in August. We had an experiment that produced 1.35 megajoules of neutron yield. This was a really big deal. It actually met the scientific definition of ignition, but didn't meet the National Academy of Science definition quite yet, which said you needed to produce more energy through fusion than you put in with your laser. So our gain was about 0.7, so we weren't quite putting out as much energy as we put in with the laser. But we were getting really close. It was an interesting experiment. Right after that, we repeated it a few times and learned a lot about the sensitivity of these implosions in this near ignition regime. I'll actually talk about those experiments more in a couple slides. But the reason that we're also interested in fusion now is because we ended up actually achieving this definition of ignition, in which we put more energy out through fusion than we put into the system from the laser back in December, so just a few months ago. So we were able to do this primarily because we got a small upgrade to the laser facility. We were able to put 2.05 megajoules of laser energy into the whole room. Previously, we could only do 1.9 megajoules, so that little bit of extra drive is all we needed to kind of get up over the ignition cliff. So that's the big news. That's why everyone is super interested in fusion research right now. I was super excited about this result, not just because ignition is exciting, but because the team that I actually get to work with expected that to happen. And I was really excited about the way we had made this prediction. So that's what we'll talk about next, is how we called it. So, as I mentioned, in 2021, we had this experiment that produced 1.35 megajoules of yield, and then we repeated it a few times. And those repeat experiments didn't produce as high of a yield as that first one. So, while some could see that as disappointing, I saw this as a really valuable data set. You know, this was the first time we'd repeated the same experiment multiple times at the NIF, and we're actually able to quantitatively say what our shot-to-shot repeatability looks like at this facility for this application. So this data set actually lets us kind of answer some super important questions, like what is the level of variability that we should expect from a future experiment, and what drives these observed variations that we see in our performance. So a group of a lot of researchers have been working to understand this data and answer those questions over the last couple of years. It's a challenging problem. There are a lot of sources of degradations in our implosions. They're very sensitive. Small perturbations can turn into like detrimental effects on the total neutron yield. So, and we can't completely diagnose our data. So we can't measure all the things we'd like to measure to really understand what's going on with these experiments. But we've been able to learn a lot by studying this set of repeat experiments. So we're using what we learned from these variability experiments to make predictions about future designs. So the process we'll walk through, and it's going to be very brief. I apologize for that. But this process is kind of a three-step process. First, we can infer the degradation mechanisms that are consistent with the data from the variability shots. So we take that set of repeat shots, we use our computer simulations of these experiments, and we basically solve the inverse problem of how do I need to adjust my code input parameters in order to match the experimental data that I'm seeing. Like, how do I need to degrade these implosions to match the data? And then once we have those input distributions for each of these individual shots, we can build a global variability model that quantifies our shot-to-shot repeatability. So it takes into account uncertainty in our model and our ability to measure things, and the shot-to-shot variations we expect from the facility and changes in the target conditions. We can then take this global variability model, which is basically just a set of input conditions that we can put into our radiation hydrodynamics codes we use to model the experiments, and then apply this distribution of degradation mechanisms to a new design to answer the question of how would this new design respond to all of the perturbations that this variability series of experiments experienced. So step one in this process is to determine those individual distributions of input parameters that describe the degradations each individual shot in the repeat series experienced. So we do this with a pretty traditional approach, Bayesian inference. If it's something you're familiar with, you basically have an inverse problem of this is what I saw in my experiment. What are the input conditions I need to do to put into my simulation to match that observation? What we get at the end of the day are these individual distributions of input parameters. If we pulled a sample from each of these distributions, ran a simulation, we would get an output that matches the experimental data that we measured for that specific shot. So that's an individual distribution for an individual shot. The next step is to stitch all of these together into a global variability model that describes our shot-to-shot repeatability. So we call this our CogSim variability model. In this case, you can think of each of these individual experiments we carry out at them as a sample from a bigger distribution, right? So this little blue set of points is one experiment that we pulled from this distribution of possible outcomes that we could have experienced at the facility. So we can take this distribution of input parameters, run them through the forward model through a simulation, and get output parameters. If we do that, we can plot, say, two outputs versus each other. Here we have the neutron yield on the y-axis, and the x-axis is the downscatter ratio. It's another measure of implosion performance that we like to look at. So if we plot the distributions from our variability model and our experimental data in these colored points here, you'd see the data lies on top of what we would expect. So now at this point, we have a distribution of input parameters that is consistent with the experimental data we measured and the variability series of shots. And we can use this distribution of input parameters, apply it to a new design and say, what does this plot look like for a new design? If I changed something about my capsule or something about my laser pulse, can I push the performance up, even when it's exposed to all of these degradation mechanisms? So that's what we did for the December experiment. We used our variability model to basically make our prior distribution, if you're familiar with Bayesian language, for our predictions for this December 4th, December 5th experiment. So we don't need to get into the details of the table, but basically use the variability experimental data, get the input distributions, and now we're going to propagate those input distributions through a forward model for the December design. I wish I could go into more details about this as well. How we forward propagated that distribution is actually pretty clever. Typically you would want to run a bunch of simulations with each of those input conditions as the inputs to the simulation. The simulations take several days each to run. It's too expensive to run thousands of those on a 1 to 2 week turnaround time. So we use some machine learning hacks to take a neural network that's basically seen a lot of simulation data, and we just run a few tens of new simulations with our new design and use transfer learning to make a neural network based forward model. And what's nice about neural networks is they're super fast to evaluate. So we can take our prior distribution of all those different input conditions, run them through the neural network, and we get a set of outputs that we expect to measure on our December experiment. So This next slide is the slide that we sent around about 3 or 4 days before the experiment actually happened back in December. So we basically said we expected the yield of that experiment to be about 2 to 3 times the yield of the shot 210808, which produced 1.35 megajoules. And we thought there was a slightly greater than 50% chance of this experiment producing more than 2.05 megajoules of energy. So the plot here on the right is kind of what we were looking at earlier, yield versus the downscatter ratio. We're comparing 210808 in orange to this December design in the blue. So we thought there was a significantly higher chance of this design performing really, really well, especially when considering the improvements made over 210808. So the experiment landed somewhere around that little yellow square, kind of right within our yield expectations, which was nice because our yield expectations were admission. So while the rest of the world was super excited about admission, I was super excited about predictive capability. Especially with uncertainties, this is kind of something our team has been working toward for many, many years. I'll summarize pretty briefly so we can get to some questions. December 5th, 2022, in the very early hours, an experiment at the National Mission Facility achieved ignition for the first time ever. We produced about 3.15 megajoules of fusion energy for a gain of about 1.5. And this experiment really built on decades of multidisciplinary and international research. Prior to the experiment, we've used a combination of statistical analysis and machine learning to quantitatively predict the outcome of the experiment. This model really takes advantage of all of the advances we've made in HPC simulations and our really nice experimental data that we get from the NIF, and combines it with machine learning. And we expected that ignition was the most likely outcome for this shot, with 50% chance of getting greater than 1. So I'd like to thank a lot of people briefly. Luke Peterson, especially, if you'd like to hear more about any of this, this was a very brief overview. You should keep an eye out for the talk that we both gave a couple weeks ago to the Data Science Institute. It'll be on YouTube in the near future, so you can hear more details about fusion and how we predicted it. And then thank a number of people who helped contribute to these slides, the Hybrid team, which is the team that designed these experiments, and then the cognitive simulation team that I work with, who made all these really awesome predictions. And then the wider, fusion enterprise, in which people have spent their entire careers and longer working toward this goal. So it's super exciting to be part of it. With that, I'm super happy to take questions. I know that was really fast.
Kelly, I have a question. Can you talk a little bit about your open source code, Gin, for training neural networks? Is it specific to a fusion application, or can you use it for other things?
Yeah, you can use it for other things. The code itself is based off this idea that selecting hyperparameters for creating a neural network is really time consuming. You could spend your entire life optimizing the architecture of a neural network. And in the ICF program, we are not machine learning experts, and we don't have a lot of time to sit around optimizing architectures. So we needed something that got the answer pretty close to right in a hands-off way. So Gen is, kind of at its most basic state, a way to automatically determine the architecture and initialize a neural network for a given data set. It does so by leveraging decision trees under the hood to determine how to make its neural network architecture. But it works very generally. We use it as a workhorse in the ICF program. It's kind of the only neural network algorithm we've been focused on, but people have used it outside of ICF as well for both regression and classification problems. So if you have a problem, a regression problem, it should be super easy to pick up that code and try it and see how it works for your data, and email me if it doesn't work.